Our next topic in modern physics is quantum mechanics. And I took, as a physics major, one undergrad course on quantum mechanics, and then in grad school, I had to take a whole year of quantum mechanics. So I've had a lot of experience with quantum, although, we're only going to get a few mini lectures here about quantum mechanics. Quantum mechanics is a branch of physics that studies the universe on sub-microscopic scales, some of the tiniest things in our universe. And this is a picture of a fly that has been taken by using a scanning electron microscope. Quantum mechanics can do a lot of things for us. One thing it helps us with is that it helps us describe the probability density of electrons around an atom's nucleus. Actually, you don't really know exactly where the electron is orbiting around the nucleus of an atom, but to some probability, you can predict kind of a cloud or a shell area around which that electron will be orbiting around the nucleus. So here are some examples of what these orbital shells look like. We're thinking about the regions where electrons have the most probability of orbiting around the nucleus. You'll find out later, but we never know with 100% certainty the position of a subatomic particle. Quantum mechanics also describes the wave-particle duality. And we kind of hit upon this earlier in the semester. I mentioned, we learned that light is a wave. I briefly mentioned that light is also a particle. So in quantum mechanics is here where we start to think about how particles can behave both like waves and like particles. So particles, both those with mass and those that are massless, have a wavelength and they behave like waves. So here we have an electron. An electron can have an associated wavelength with it. An electron is a particle. The photon is our individual quanta of EM, electromagnetic radiation. The photon is actually massless. It has no mass. We can represent the photon, we can think about the photon as being a particle, but we can also think about the photon as having a wavelength too, where electrons, since they have mass, can approach the speed of light, but they can never travel at the speed of light, but photons are always traveling at the speed of light. Our story of quantum mechanics really begins with the German physicist Max Planck. And he hypothesized that atoms or molecules can act like oscillators to absorb or emit radiation. And these oscillators, kind of think about them as being connected by springs. And we talked about oscillation previously in first semester of our physics course. These atom molecule oscillators were only allowed to have certain discrete energies. These energies equal to h times f. F is our frequency of oscillation, and h is what we call the Planck's constant. And Planck's constant is 6.626 times 10 to the minus 34 joule times second. Planck deduced that energy is therefore quantized, and so thus began a new branch of physics, quantum physics. So this energy is quantized, meaning that these energies of these oscillators can only take on certain energies that equal to the frequency of that oscillation times this Planck constant. This idea that energy is quantized is very well represented in spectrum, emission spectrum or absorption spectrum of gases and elements. Here we have the emission spectrum of oxygen. And what we're looking at are these bright lines here. Underneath them, we have the continuous visible spectrum. And what we're really looking at here are these emission lines of oxygen. Those are these bright lines. here, 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 and so on. So what happens is that you have this tube of oxygen gas, and you send an electric discharge through this tube. And whenever that happens, the molecules of the oxygen gas absorb energy, and then that energy is re-emitted as discrete, specific electromagnetic radiation with specific wavelengths of light. Emission is the process by which a higher energy state of the molecule becomes converted to a lower one through emission of a photon, and that results in the production of light. So this implies that the energy states of the atoms and molecules are quantized. And in particular, the photon energy of the emitted photon that creates these distinct emission lines is equal to the energy difference between the higher energy state and lower energy state of this oxygen gas whenever it's excited by this electrical discharge. So these atomic spectra that show us these distinct spectral lines are very important analytical tools to help us understand that energy is quantized. You can think about a photon as being a quantum of electromagnetic radiation. Photons are our individual packets of light. They come in discrete packages. The energy of a photon is given by this equation here. The energy is equal to the Planck constant times the frequency of the photon. When we were talking about waves, we said that the frequency is equal to the speed of the wave over its wavelength. So if our photon travels at the speed of light, then the frequency is the speed of light divided by the wavelength. So the energy of our photon is equal to the Planck constant times the frequency, which is equal to hc over the wavelength of the photon. When we're working with these really small systems, it's sometimes more useful to use the unit of electron volt instead of the joule. The electron volt is a much smaller unit than the joule, and that makes sense when we're dealing with these small systems. So you can rewrite the Planck constant in terms of electron volts. The Planck constant is 4.14 times 10 to the minus 15 electron volt seconds. And conveniently, we can also write H times C as 1,240 electron volts times nanometers. So that's a really useful unit here, especially if you're going to be dealing with wavelengths of light in the visible spectrum that are going to be given to you in units of nanometers. So then you don't have to convert your wavelength to units of meters. If it's given to you in units of nanometers, and we know H times C, an electron volt over nanometers, you can just take this quantity, put it up here, divide it by the wavelength, then we're automatically going to get the energy of the photon in electron volts. So over here, we've got the representative energies for submicroscopic quantum effects. And we was thinking about the order of magnitude. The energy of red light, for example, is 2 electron volts. So you can talk about the energy of visible wavelengths of light in terms of electron volts as well. Here's our electromagnetic spectrum, and we can relate the wavelength of the wave to the energy of the photon, and we can also think about the frequency here. So in this graphic, we have the wavelength of the light on top here. We've got the energy of the photon here, and we have the frequency of that light down here. We've got radio waves, our longest wavelengths of light over here on the left in this graphic. We've got our longest wavelength waves. They have the lowest frequency. they also have the lowest energy for that photon in electron volts. And then we come through here through our visible part of the electromagnetic spectrum, which remember is only a very tiny swath of the entire electromagnetic spectrum. And then over here, we have our shorter wavelength waves. Those are our X-rays and gamma rays, way above violet on our electromagnetic spectrum. Shorter wavelength waves have higher frequencies, and our shorter wavelength waves actually have higher energies. And so if we're comparing the energy of the photon for a gamma ray, for example, to the energy of a photon for radio waves, we see that those energies vary greatly over many orders of magnitude. This particular gamma wave with a wavelength of 3 × 10⁻14 meters, very short wavelength, has an energy associated with it of 41 mega, that's big M, mega electron volts. And then when we go down here to our longest wavelength waves, down in the radio wave part of the spectrum, long wavelengths of 3 × 10⁶ meters, that's quite long. And they have the smallest energies. The longest radio waves, the longest wavelength radio waves have energies on the order of 10⁻13 electron volts. Now, photons have no mass. Our electrons, our protons, they all have mass, but photons are massless. Despite having no mass, photons actually do have momentum. And the momentum of our photon is, the momentum of the photon is equal to Planck's constant divided by the wavelength of the photon. In our classical depiction of momentum, momentum is equal to the mass times the velocity of the particle. Our photons do not have a mass, so we can't calculate the momentum of the photon in the same way. And also our photons are always traveling at the speed of light. The momentum of a particle changes if it has mass and is traveling very close to the speed of light. It differs by a factor of gamma, like we were talking about in our mini lectures about relativity. Let's say, for example, you have an electron that is traveling at times 10 to the 3, 10 to the 4, 10 to the 5 meters per second. It's still a fairly decent approximation to use the fact that the momentum is equal to the mass times the velocity. Only when your particle with mass that is traveling very, very close to the speed of light do you have to start worrying about the relativistic effects, like we talked about when we were thinking about special relativity. We can use the momentum of a photon to our advantage. One example is something called a solar sail or a space sail. Space sails have been proposed that use the momentum of light from the sun, those photons coming from the sun, reflecting from gigantic low mass sails to propel spacecraft through the solar system and beyond. So here's a schematic of what these solar sails might look like. There is a proposed project called Breakthrough Starshot, which proposes to use solar sail technology just like this to propel a tiny fleet of spacecraft to Proxima Centauri. Proxima Centauri is the nearest star to us beyond the sun. It's 4 light years away. A light year is the distance that light can travel in 1 year. So the idea is that you create a bunch of these solar sails and you attach a very lightweight, tiny kind of little telescope onto the end of it, kind of like this. And then from Earth, for the Breakthrough Starshot proposal, you shine a bunch of high-powered lasers instead at these sails, and then you're imparting the momentum of the photon from those lasers into the solar sail, and that can help to propel that sail through the solar system and then out eventually of our solar system toward the star Proxima Centauri. Now we're going to walk through a problem where we compare the momentum of an electron to the momentum of a photon.
For the first part of this problem, calculate the momentum, P equals question mark, of a visible photon that has a wavelength of 500 nanometers. Okay, so our photon, the momentum of a photon, the equation to give us that, P is equal to h, our Planck constant, divided by the wavelength of the photon. Now, we cannot use the standard classical description of momentum here. Momentum is equal to mass times velocity, because photons are massless. Since photons are massless, we have to use a different equation here in order to find the momentum of our photon. Now, this is going to equal, so you have two choices. You can use the Planck constant in units of joules times seconds, or in units of electron volts times seconds. But it makes more sense to use the unit, I think it makes more sense, to use the unit of joules times seconds here for the Planck constant. So that's 6.63 times 10 to the minus 34 joules times second. And we're going to divide it by our wavelength here. And our wavelength was 500 nanometers, or 500 times 10 to the minus 9 meters. And that will give us a momentum of 1.33 times 10 to the minus 27 kilogram time meter over second. Okay, so how did we get that unit out of here? And maybe this also explains why I use joules. So a joule can be written as a kilogram meters squared over seconds squared. And we're multiplying it by time, by unit of second. Oh, we're not really multiplying it by time, but we're multiplying it by a second, which is a unit of time. And then we're dividing it by a unit of length, meter. So here, let's see, I've got a second here that cancels with one of these seconds. I've got a meter here that cancels with this meter. That leaves me with units of kilogram time meter over second. And that's a standard unit of momentum. So I'm good. For part B, find the velocity of an electron having the same momentum. Okay, so V equals question mark for an electron with P is equal to the same momentum here. All right. So because an electron has mass, we can use our standard definition for momentum. Momentum is equal to mass times velocity. We need to solve this for the velocity of our electron. So we divide both sides by m. Divide both sides by m. So this tells me that V is equal to the momentum divided by the mass of my electron. So the momentum we want to use, our question says, find the velocity of an electron having the same momentum as our photon. So we have to use this momentum that we just found from the photon here, 1.66 times 10 to the minus 27 kilogram time meter over second. And then we're going to divide it by the mass of an electron, which you can find off of your equation sheet. The mass of the electron is 9.1 times 10 to the minus 31 kilogram. Okay, the mass cancels here and here, units of mass, and that gives us a speed of 1.46 times 10 to the 3 meters per second. That's also 1,460 meters per second. That's how fast this electron is going to have the same momentum as our photon. Now for part C. What is the energy of the electron? So we'll be looking for the kinetic energy of my electron. What is that? And how does it compare to the energy of the photon? So compare to the energy of the photon. We already found earlier, oh no, we didn't yet find the energy of the photon. So we're going to have to calculate both of those. Okay, so the energy for our electron, let's do this here. Let's find the kinetic energy for our electron. And that's going to be kinetic energy is equal to 1/2 mv squared. So that will be 1/2 times the mass of my electron, 9.1 times 10 to the minus 31 kilogram. And then I multiply it by the velocity of this electron, which is the electron that has the same momentum as my photon. And so we've got to multiply it by 1, we'll put it in scientific notation, 0.46 times 10 to the 3 meters per second. That gives me a kinetic energy of my photon of kinetic energy, this is of my electron, 9.7 times 10 to the minus 25 joules. Okay. But you know what? I'm going to go ahead and get this in units of electron volts. So I'm going to convert this from joules to electron volts. So 1 electron volt is 1.6 times 10 to the minus 19 joules. Okay, and that gives me a kinetic energy of my electron in units of electron volts of 6.06 times 10 to the minus 6 electron volts. Okay, and now we want to compare this to the energy of my photon. Photon energy. And again, photon is massless. So we can't use our standard equation here for the classical description of energy for our photon. We have to use the equation E is equal to Planck's constant times the speed of light, all divided by the wavelength of my photon. Now, there's a really handy conversion for you for what is Planck's constant times C on your equation sheet. Actually, the front page of your equation sheet has H times C in units of electron volts times nanometer. That's going to be really useful for us here. So H times C is the same thing as 1,240 electron volts times nanometer. And I will leave it as an exercise to the reader, which is what they used to say in physics books when they're like, I'm not going to derive this for you today. You could try to work out and prove to yourself that Planck's constant times C does give you electron volts times nanometers, 1,240 electron volts times nanometers. And we're dividing by the wavelength of our photon, 500 nanometers. My nanometers cancel here and here. I'll get the energy of my photon in electron volts, and that turns out to be 2.48 electron volts. Wow. So we have the energy of my photon with the same momentum, 2.48 electron volts. The energy of my electron with the same momentum, 6.06 times 10 to the minus 6 electron volts. So if I divided E photon over E electron, so the energy of my photon divided by the energy of my electron, if I took 2.48 electron volts and I divided it by 6.06 times 10 to the minus 6 electron volts, I will find that there's a difference of these of 4 times 10 to the 5, of magnitude 4 times 10 to the 5. So the energy of my photon with the same momentum is 4 times 10 to the 5 times greater than the energy of my electron with the same momentum.